All right, we are rolling. Let's do this thing. We are talking about parent and piecewise functions. We're going to start this lesson with the ladder, piecewise. But Mrs. Contreras, let's just go ahead and jump right into this. Can you read to us what a piecewise function is here on the page?
Piecewise function is a function which is defined by multiple subfunctions, each subfunction applying to a certain interval of the main function's domain, which is something that we also call a subdomain.
So we have a function that has functions within it. And what's important is it is a function. So these functions are not overlapping. These sub-functions are not overlapping. One thing that you can notice right away is that we move up to -4 from the left-hand side in the domain. And then notice there's an equal sign here. Right? This x plus 5 sub-function is associated with the number 4. -4. Right? The function 3, not associated with -4. There's no equal sign. So that's something that we need to notice right away. Let's graph this thing.
So x plus 5, that's a line. It has slope 1, and it is in slope-intercept form. So we do have our intercept is at +5 for our y-intercept.
All right, but I'm gonna stop you real quick because can I plot this point?
No, because it's not in the domain of that subfunction.
It's not in the domain of that. We don't want that. I mean, maybe you use it to graph the function and then delete what you don't want. We could do this. We could go there, and we got a slope of 1, so we could go down, and then we use those points. But I have a better idea. Right? Let's plot x equals -4. What would that be? Just plug it into this subfunction.
So our point would be -4, 1. If we just plug in -4.
So plug in -4, we get -4, 1. We have the endpoint of this line now. Once again, slope-intercept form, it's lame. It requires you to use the y-intercept, but the y-intercept is not always important. So I recommend that you just plug in some points. We call this point plotting, and we're going to use this a lot in this video here. We're going to figure out what graphs look like by just doing it old school, plotting points, and then noticing patterns, which is what the essence of math in some ways. Give me another point on this line, the sub-function, x plus 5.
-5, 0, I think that works.
Cool. And then write 2 points, define a line. So we're done, I believe. You just need to actually graph it. And let me actually do a good job graphing it. Oh, I'll take your tip, and I will use the drawing tool. Nice. Oh, right, that should have been 45 degrees. I think it was 44. Don't tell anyone. Let me go back to the drawing tool. Let's draw this second function, 3. How is that a function? That doesn't even make sense.
A horizontal line at 3, at y equals 3.
No matter what value you give me between -4 and 2, not including -4, that is not, there's no equal sign there, you're going to get 3. So -4, -3, 3, or -3.5, 3, -1, 3, 0, 3. I think 2 is included. All right, what am I doing as I get closer and closer to -4 though?
We can include everything up to -4, but we have to have an open circle at the point -4, 3.
All right, and that's the way. Yeah.
Well, because we have this subdomain is not including -4.
Well,
nice.
Right. We're graphing a piecewise function. I don't know why they call it piecewise and not just like a. I guess that's better than anything, I guess, or as good as anything. Let's proceed. We got one last thing. We got 2 to 8, -2x plus 7. Once again, that intercept is useless to us because this is not defined at 0. What are your thoughts?
Yeah, I agree. That's pretty useless. So I guess we can just plug in a point and then go from there with our slope.
I think there's 2 points that you can plug in that are quite convenient because we know this is a line. What happens when I plug in 2?
Plug in 2, which is the end of our subdomain, and then we get 3.
Sweet. And so should I put a hole there?
Well, actually, I don't know. What do you think? Because
Well,
like when we're drawing that, if we were to just like draw from left to right, then for the first part we would have to like pick up our pencil and then make an open
Yeah.
circle and then draw. But
I'm here.
it feels
I'm
kind
here.
of redundant to put an open circle over top of a closed circle.
Yeah, I don't think we need to, because that's like almost misleading. Like, is there a point there or is there not? There is. Let's just put a dot or no dot, but certainly not a circle, because there is a point there, and circles mean that there is no point. All right, and so we plugged in 2 when we got, so if I plug in 2, I get, for this function, I get 3. What do I get when I plug in 8?
Plug in 8 and you have negative 2 times 8, which is negative 16 plus 7 is negative 9. And that still fits on our graph because they're
Yeah.
negative 10 to 10.
Let's get that circle there because we are not including 8. And then let's get our line tool. And we encourage you, when you guys are doing this in Kami, to use that line tool as much as you can. I know it's difficult. We have a pencil to draw, but you guys might not have that. So take advantage of the line tool whenever necessary. But there we go. I mean, we could have used the slope, like you're saying, and that's absolutely reasonable. But I think it's a cool little trick to just get your 2 endpoints, whether or not they actually exist, 4 lines, and then just connect them with the line tool or with your pencil, with the ruler.
Cool.
And look, I believe our slope is emphasized here. Down 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1. Cool. Okay. This is a piecewise function. Right. Is there anything you want to add here, Mrs. Contreras, about piecewise functions before we knock out the domain and range?
I think it's interesting to note that for one part of this, we have something called a discontinuity, and it's a jump discontinuity because going from one to the other, you don't have anything that is the same, right? If you're looking at it coming from, if you're approaching, what is that, negative 4 from the left versus approaching negative 4 from the right, you're getting totally different numbers. So that's something that we can call a discontinuity. But it's also interesting that we don't have a discontinuity at x equals positive 2, because as we're approaching positive 2 from the left versus the right, we're still getting the same number, which is nice.
Yeah. So we will rigorously define those words in a future lesson. In this unit, discontinuity, continuity, lots of other terms too. But these are really important terms, and these will come back over and over again throughout your math career, particularly in calculus. Hence, we're learning it in precalculus. All right. Real quick, what's the domain?
Our domain is from negative infinity to positive 8, not including positive 8.
Not including positive 8. And yeah, there we go. Yeah, because no matter what number you pick in here, there is a y value associated. And what's the range?
We're going from negative infinity because that first segment goes all the way down to negative infinity. And we're going up to 3.
Yep, and we are hitting, so you might think, oh, we're going up, we get to 1, and then we skip to 3. If we were going from negative infinity to like 0, that would be the case. The range does not include 1 to 3. But we hit those points over here, so we are good. We are going to 3. Awesome.
I don't know if you're trying to point with your cursor, but I totally can't see it.
Oh, I forgot that that's a thing. That's annoying. All right, I was. But with all that said, let's proceed. I had a parenthesis. I turned it into a bracket, by the way, everyone. Hopefully you noticed that. Is this 1-to-1?
No.
No, it fails the horizontal line test. All right, the vertical line test for functions, horizontal for 1-to-1 functions. So
especially because we have a horizontal line as part of our piecewise function.
Yeah. So like if I said, hey, I have 3, what number did I plug into the function? There are multiple answers to that question. I could have.
It's like an infinite number.
There, absolutely. So here's a little challenge problem for everyone. We're not going to do this one, but we'll ask a question here. All right, but try to knock this one out. Give us the subfunctions of this piecewise function. And there will be, I'm assuming that there will be some controversy here. And what's happening there? Like, play around with this one, and we'll talk about a similar problem like it in class. But good luck with this one. Write the rule for this piecewise function. Right?
So maybe we could say write a rule, because there could be multiple rules.
Yeah, that is true. Yeah. So there are 3 sub-functions. But we'll let you guys do that one. Let's proceed. Right, piecewise functions. We're going to move on from this. We'll come back to it at the end. But it is a function with sub-functions. Looks a little bit different than your parent functions, which tend to be smooth. Parent functions. Mrs. Contreras, can you read to us what a parent function is?
A parent function is the simplest function of a family of functions.
All right, so this first one here, x squared. What do we call that thing?
Parabola.
The parabola. Right? There's lots of parabolas. This is our parent parabola. So parabolas can look like x squared, but they can also be like 2x squared, be a little bit more narrow, or like 0.001 x squared, be a little bit more rounded out and flat. And so a parent function is that function that we use to help us then graph more complicated functions that look like it. So x squared. Let's just knock this thing out. Let's figure out what it looks like. Right? Many people already know what x squared looks like, but I'm sure that in this lesson you'll notice a function that's new to you. X squared. What do you want to plug in?
0. I like 0 starting there is good.
Yeah, 0. Yeah, 0.
And then 1, maybe -1.
1, -1. Already, this is not a one-to-one function. You know what? That's one of the questions here. Let's just knock it out and say no. Right? When I have 1, it's coming from 2 different things. How about -2?
That sounds like a good plan. It's a 4, right?
Yep. And 2, and then 4, and then -3. I think is the last one we can fit on this graph. And I recognize that the viewer is going to have a hard time doing this on their own, on their computer. We encourage you to, if you're taking notes, or if you're doing this, if you're doing the assignment in class, to print out this assignment so you can actually put pencil to paper, right? One could just, a teacher could just say, hey, graph these and look at them and then appreciate them. We want you to put pencil to paper here so that not only do you know what the graphs look like, but you also know important points. Right? When I say in the future, graph x squared, you just want to knock it out. -9, -3, 9, -2, -2, 4, -1, 1, so on and so forth. You want to recognize these important points. These points that meet at the intersection of grid lines. All right, what's the domain of this thing?
All real numbers.
All real numbers, range?
Non-negative numbers.
How do you want me to write that? That's a fun set to write.
Well, we could do R plus and union 0, or we could do R minus R negative.
Ooh, I kind of like that one, but it doesn't matter. R, I'll do this so people can see the backslash. R minus, this is kind of like a removal symbol for sets. R minus. So that's saying all the real numbers and then take away all the negative stuff. Cool. Have fun with how you answer these questions. Like, don't feel boxed into a certain format. Let's get x cubed.
0, 0.
0, 0.
1, 1.
1, 1.
-1, -1, because we're cubing, so then our negative doesn't get exponented away. 2, 8.
2, 8. So this one grows way faster than, well, I guess it's all relative, but this one does go faster than x squared.
And
right?
yeah, -2, -8.
Yeah, I got that one. So my question to you, just with this graph, I think this is important to notice, and we'll emphasize this in the lesson, in class, when you guys are looking at this function in a closer up. But what's happening between -1 and 1? Is it like a straight line?
I don't know. Because, like, think about if you have like 1/2 and then you're cubing it, then what do you get out?
You get 1/8.
But then if you have like 1/4 and you're
cubing
it,
right? 1/64.
Which seems a lot smaller.
Yeah, what I think is happening is, and We're not going to explain why in this class. You will receive an explanation. Maybe you'll come up with that explanation on your own. But this has a slope of 0 at 0, 0. We like to talk about this thing in a future class called instantaneous rate of change, right? The instantaneous slope at a point, it's going to be 0. So when you graph the x cubed graph and the x squared graph as well, and the x to the 4th and x to the 5th, and any polynomial at 0, the parent function, you're going to have a slope of 0 there. So that's important because we have other functions that look like this, the tangent function, that does not have a slope of 0. So we want to differentiate it as well from other functions. Domain.
All real numbers.
Boom. Range.
All real numbers.
Awesome. This one's better than x squared in that facet. And then 1 to 1.
Absolutely.
All right, here we go. X to the 4th. Ooh, it's bouncing around a lot. Let me use my stroller. That's better. All right, x to the 4th. Let's knock it out real quick.
0, 0.
0, 0.
1, 1.
1, 1.
1, 1.
Mm-hmm.
2. Oh boy. It doesn't.
16, right? Yeah, it doesn't even fit. So like I need to like leave the graph right here. All right, so this one is super narrow. And then you're going to explore this a little bit more in class, but I'm going to make it actually a little bit more rounded at the bottom. You can look up y, or you can plug in values to see y, but it's a little bit more rounded at the bottom. All right, so this one.
Oh, it's quartic, right?
Yeah, this is a quartic. Ooh, let's throw that down there. Quartic. This is quintic. Quintic. All right, and in marching band, we call the instrument with 4 drums quads, and we call the instrument with 5 drums quints. Just for fun. All right, we didn't get the domain and range of this one, but this one is all real numbers. The range is all the real numbers minus the negative real numbers. All right, there are probably better ways. You know, you could just say 0 to infinity. That might be better. And then 1 to 1, no. Over here, x to the 5th. When you plug in 0, you get 0. When you plug in 1, you get 1. Right? Notice that all 4 of these graphs have this property. Think about what's happening in between -1 now, and you'll be ready for class on whenever this video is proceeding. And then when I plug in 2, that's 32. So same thing. Let me go out right there. All right, once again though, it's going to be flat there in the middle. If you want a better visual of this graph, maybe throw it into Desmos. But once again, we really encourage you to actually put pencil to paper here and internalize these points of interest. Domain, all our numbers, range, all our numbers, 1 to 1. Yes.
Yep.
All right, those are our parent polynomials. We're going to move away from polynomials and look at some more specialized graphs. All right, we have the absolute value graph here.
Should have a function dance.
Oh, you know, we didn't do the function dance. All right, what's a line? What is a cubic? Or no, sorry, quadratic. What is a cubic? Oh, I think I have to switch it. Wait, no, my camera's reflected. I don't know. What's to the 4th? What's to the 5th? What's to the 6th? What's to the 7th? Now do it all at once. Ready? 1 and 2 and ready. Here we go.
Now you're reflecting it. Wow, it's getting advanced. It's transferring.
Wait, I was doing this. I was not doing this. I should have been doing that. All right, I digress. Let's move on. We got the absolute value graph as we previously said. Plug in some numbers. Let's know what this looks like.
0, 0.
0, 0.
1, 1.
1, 1.
-1, 1.
-1, 1. So this is a parabola again?
No. 2,
No.
2.
2, 2. 3, 3.
-2, 2. Whoa, you're getting a line.
And I'm going to take advantage of my line tool. Make sure that that slope is 45 degrees. Oh, I got 44.9. 45.1. It's not perfect. That's okay. Perfection is not a requirement. Let me go back to the drawing tool though. Here is our absolute value function. You know who needs a V, a victory? The Eagles.
Ooh.
All right, go Birds. What's the domain range, and is this one-to-one?
Domain is all real numbers. The range is including 0 to infinity, and it is not 1-to-1. Nah, bro. It's not academic language, but okay.
Yes. Move your hat to backwards mode. Look, it still says Eagles.
Oh, nice.
Nice. You can't avoid the eagle. Okay. There we go. We get the absolute value function. Now let's get the square root function. All right. You may recognize this from geometry class. What does the square root function look like?
0, 0.
0, 0.
1, 1.
1, 1.
4, 2.
4, 2.
9, 3.
9, 3. And you're just getting these points from plugging them in, right? Like you're just. Yeah.
I just wanted to use perfect squares because it's just too much effort to try to ask you to plot where irrational numbers are. It's excessive.
Yeah. And a fun fact, if you're not taking the square root of a perfect square or the ratio of perfect squares, that number is irrational. Have fun with that. What was I saying?
Domain is
well, before we do that, just I want to remind everyone. Let's rewrite this equation as y equals the square root of x, right? Y instead of f of x, only because this is something that you might be familiar with. I'm going to square both sides. Right? Notice that when I square both sides, weird things happen. We've dealt with this before. You get extraneous solutions. We have y squared equals x. That is a parabola that has been rotated 90 degrees. Right? You dealt with that last year in your conic section unit. Right? So this should be a parabola that's been rotated 90 degrees from that previous function. The problem is it's a function, and we can't get two values. And that's why it's necessary that you check for extraneous solutions when you solve equations, because squaring is something that changes the properties of an equation. Right? But just a fun fact, this is a parabola, but only half of it. The negative half, actually. Well, it's positive here, but it's the part that we're getting is the negative half of, come on, Ben. The negative half of the square function. Sorry, the parabola function. All right, domain range in 1-to-1.
Wait, is it a negative? I don't know. If you think about it as a rotation, yes, but if you think about it as a reflection, no. Then it's the positive part, right? Because if you're thinking like this is the positive part and then you reflect it this way, then you get your.
Which you're totally right, because something that we'll talk about later is switching the x and y is a reflection of the line y equals x. For those who want that information now. So you're absolutely right. I am false information.
Fake news.
Fake news. Hit me with the domain range in 1-to-1.
Domain negative, no, 0, including 0 to positive infinity, and the same thing for the range. 1-to-1, yes.
Yes, excellent. Ooh. Give me some points. Give me some points. We got the
0, 0.
Cubic root.
0, 0.
1, 1. 1.
Negative 1, negative 1.
Oh, okay, okay. So this is about to be this?
Maybe not. Because what if we plug in a perfect cube like 8? We plug in 8, and we get out 2.
And then we're going to get a negative number. Right? This is the cubic function reflected over the line y equals x, once again. Right? What we just dealt with this, the square root function. Right? These are all related to each other. I'm going to have an undefined slope at 0, 0. right?
Nice.
Yeah, there we go. And that's not that poorly drawn. Domain range and 1 to 1.
All real numbers, yes.
I'm struggling with my stroll bar today, by the way, if you haven't noticed.
It's okay, hang in there.
Go over there. Domain, all real numbers. Range, all real numbers. And you said 1 to 1?
Yep.
Yes, awesome, right? When the answer to this question is yes, that is an operation that you can do to an equation and not have to check for extraneous solutions, by the way. Right? If I have an equation, the cubic root of x is equal to 8, and I raise both sides to the third power, I'm not going to get extraneous solutions, right? Because it is a reversible operation. It is 1 to 1. You can go back to the thing that it came from because there's only one thing. So that's an important attribute of function. That's why we care about it so much. Ooh, here we go. Here we go. Here we go. The fourth root of x squared. Give me some points. Give me some points.
0, 0.
0, 0. Love it.
1, 1.
And let's take ourselves through this. When you plug in 1 into this, you square it, you get 1. You hit the fourth root, you get
1.
When you plug in -1, you square it, you get
1.
1. And then you take the fourth root, you get +1. Don't forget, principal root. The principal root is your pal. And so is Miss Johnson.
Miss Johnson is awesome.
What happens when you plug in number 2? Not 2. Let's go with 4.
4. Okay, so 4 squared, that's 16.
Mm-hmm.
And then the fourth root is 2.
2, right? Yeah. -4?
-4 is same thing, right? Because -4, when it's squared, you get +16. And then once again, the fourth root is 16, +2.
Yeah, and only +2. And then if you plug in more things, I mean, we can also plug in, I think, 9, right? 9 squared is 81. The fourth root of 81 is 3, right? We are getting a square root function here, which is like kind of intuitive, right? Because if you simplify this fraction, what would it be? It would be that, which is x to the 1/2, right? But we can't simplify because we are changing the function by doing that. Right? This is the fourth root of x squared. We can plug in negative numbers into this thing, and we are going to get what I like to call, well, let me get this point right here. The eagle function.
Power of the eagle.
Stop it. I'm being recorded. Good. All right. So we got the eagle function here, the fourth root of x squared. I call it the eagle function because it looks like one of those birds that you draw on a painting. With infinitely long wings. Because that's what we do.
Yes. The film special.
Domain range 1 to 1 of the eagle function. This is totally
domain, I think, is all real numbers.
Okay.
Because we can plug in all the negative numbers that we want, right? It's pretty great. The range is going from 0 inclusive to infinity.
Gotcha.
But it is not 1 to 1 because there's 2 wings.
But that's okay because it's still the eagle function. It's like, oh, it's not too early. I'm probably pissing off neighbors, but it's not too early. It's not like 6 a.m. All right, let's proceed. I know we're all sad that we're leaving the eagle function, but it'll always be there for you, even when you give up 27 points in the unanswered points in this third and fourth point. So 2 to the x, 3 to the x, we call these exponential functions because the variable is in the exponent. Let's plug some stuff in and figure out what these look like.
So if we plug in 0, then 2 to the 0 power, or anything to the 0 power for that matter, is just 1. So actually we have it for the 3 to the x also.
Let's do these concurrently.
Cool.
Throw some vocabulary at you at the
If
same
we plug
time.
in 1, then we get just the base because it's 2 raised to the first power, that's 2, or 3 raised to the first power, that's 3.
So this one looks like it's growing faster over here.
It does.
Right?
It really does.
All right, so let's plug in -1. What do you get?
If you plug in -1, then you get the reciprocal, right? So then it's 1/2 to the first power, which is 1/2,
Yep.
or 1/3 to the first power, which is 1/3.
All right. Okay.
And then after that, I mean, like, we can talk about it, but I don't know if your pen is fine enough to do it.
I mean, there might be. Oh nope. I could go to 0.1, but we're not going to do that. All right. Can we get any other points on this one? 3 to the 3. 3 squared is 9.
That's 27. I think that's kind of out of it.
Well, I'm doing 3 squared. 3 squared.
Oh, 3 squared. 3 squared. Yeah.
That's 9.
That's 9.
We got that. We got that.
And after that, yeah, you can't do it.
Over here, we got 2. Let me get rid of this stuff, by the way. Boom. Then we got 2 to the 2 squared is 4.
2 squared is 4. It's not
And 2 to the 3 is 8. So this one we can get a lot of good stuff. And the other side is just going to be the fractions of those, 1/4, 1/8. There we go. What happens is I go to the left on both these graphs, though. I mean, I can't really graph accurately the points, but I can talk about what it's getting towards.
Yeah, because as we're finding like smaller and smaller fractions, right? That's pretty much what we're doing. We're having 1 over bigger and bigger numbers. That as we increase the power in our like denominator of 2 that we're looking at, we're gonna get not negative though, right? Positive exponent. Then we're getting numbers that are closer and closer to 0. So we could say that it's we have a horizontal asymptote. Or we have end behavior that is going to 0.
Yeah, so let's actually draw that end behavior. Let's draw what we call an asymptote. And we haven't rigorously defined what an asymptote is, but we will do that. But in a nutshell, we're going to draw a dotted line to represent the line that we're getting closer and closer and closer to. And once again, to throw some prior knowledge back in your brain, everyone, when you did hyperbolas, you had slant asymptotes. The hyperbolas got closer and closer to these diagonal lines. So you might have some experience with asymptotes, but as we get closer and closer, as we get bigger and bigger negative numbers, we're going to get closer and closer to 0. Same thing over here. You're never going to get to 0. Isn't that sad? Like imagine that was like a sandwich that you really, really, really wanted. It's at 0. You never get to it. That's unfortunate. What's the domain range in 1 to 1?
Domain is all real numbers because you can put any number into the exponent. The range is not including 0, but going up to infinity because we have that sandwich sadness going on at 0. But we can grow to infinity, so that's nice. And 1 to 1, I think, yes.
Yeah.
Looks like it's 1 to 1.
A function does not have to have a range of all real numbers to be 1 to 1. I believe that's the pattern that we were starting to notice. But this is a counterexample to that. We could ask the question, does a function need to have a range of all real numbers to be 1 to 1? Cool. All right, so I believe if I shorten a little bit further, we're going to get 2 more kind of miscellaneous functions. Right? The 1 over x function, and what the heck is that other thing? Let's get to that in a second. Well, the 1 over x function, let's do this one quick.
So we actually can't plug in 0 because then we get undefined, so that's a bummer. But, you know, we can, like, in our minds, I guess we can plug in, like, 1/10. So 1 over 1/10, and we get out 10.
Boom.
Which is, yeah, the end of our thing. And then
we could plug in 1 billionth, right? And get 1 billion. So that I'm going to add an arrow here because we are getting infinitely large. We're just never going to get to 0. That if the vertical asymptote, if that was a sandwich, you'd never have that sandwich. Keep going.
Plug in 1 and you get out 1 because 1 over 1 is 1.
Very steep. Okay.
Plug in 2 and you get 1/2, and then you just get smaller and smaller fractions.
1/3, 1/4, 1/5. When you plug in 10, you get 1/10. Right, so there's some reflection going on here. When I could have drawn this better. When I plug in 1/2, I get 2. I was a little bit off there. My graph is something to be desired, but perfection isn't necessary. Right? And then we're done?
No, because we can also plug in negative numbers. So we can plug in all of those same numbers we plugged in. -1 gives us -1. -1/2 gives us -2. And so on.
So on and so
Negative
forth.
billion.
Fun fact, This, I just mentioned hyperbolas. This is a hyperbola with vertical and horizontal asymptotes. This is a hyperbola that has been rotated. Its axis of symmetry has been rotated 45 degrees. We're not going to get into that, but that's kind of cool. A hyperbola. We just talked about it a second ago with asymptotes. We have asymptotes here. Domain, range, and one-to-one.
Domain and range are all real numbers except for 0.
Ooh, so except for 0. Or we could do negative infinity to 0, parenthesis, union, parenthesis, 0 to infinity. That's a little bit cumbersome. I like this. Range?
Range is the same.
Range is the same. Yeah, because look, I don't think we should go over this too quickly. Right? Clearly, when we plug in 0, we're not going to get anything. We got undefined. Well, I drew a sad face earlier. I guess that's not mathematically technically correct. Don't tell your parents that sad face. We can just define in this class that sad face is congruent to undefined. But that's for another day. Right? But I don't think it's as obvious that when we can't get 0. Like 0 is not in the domain. Can you kind of talk to me about? Well, we've already kind of talked about it, but sweeping up.
Because if you're looking for 1 over x to equal 0, like how would that happen if you're plugging in non-zero numbers into x? Like as big of a number as you can plug in, you're going to get very close to 0, like 1 over a billion. That's going to get very close to 0, but you're not actually going to get out 0.
It's impossible to get, so it can't be in the range. I have an equation right here. If I try to solve this, multiply both sides by x, 1 is equal to 0.
That breaks math.
That isn't a that is not an equation. It's not a fact. All right, so we do not have 0 in a range. All right, one-to-one.
I think so.
Yeah, this one is like kind of deceptively one-to-one, but for sure one-to-one, right? I challenge you to try to find a number that is coming from 2 different things. Right? It doesn't exist. All right, so this is a hyperbola, but we generally just call it the 1 over x graph. Do we have a name for this besides hyperbola or 1 over x?
1 over x, I don't know.
Yeah, I think that's just it. I think that's what people would generally call it. Let's go over to this one though. All right, before we do this, I want to approach it like we did that problem earlier on the first page, the parabola. Let's rewrite this as y equals the square root of 25 minus x squared. Let's try to turn this into something that maybe we recognize. Let's square both sides.
I think you lost a x squared.
I did, thank you.
Okay.
Oh, right there. I don't want to forget. We got y squared is equal to 25 minus x squared.
Oh, and then we can move that x squared over to the other side, so we get y squared plus x squared equals 25, and that's a circle, right?
That's a circle.
Radius 5, because
circle radius 5.
X squared plus y squared equals 5 squared.
Yeah. All right, so we know what this graph looks like from prior knowledge. The problem is the circle, which you guys in the last homework assignment, the last classwork assignment, hopefully claimed is not a function. So what's going on here?
Well, we're looking at the square root of 25 minus x squared, so that's the principal root. So we're only looking at the positive side of our circle, which is kind of like a sunrise or a sunset.
So let's plug big things in and only get the positive stuff. So we're going to get that circle, but only the positive stuff. Negative 5, 5, right there. I'm doing this one in pink, just because pink is great. And it's wet.
And it's Wednesday.
Yeah.
Oh, wait. Are we supposed to say that? What day is it? I don't know.
It's Sunday. I said Sunday on the day. Whatever. All right. Can we verify that this is, in fact, a circle, though? Plug in some other points that are going to fall in the intersection of grid lines.
What would give us perfect squares? Well, if we wanted 25 minus something to give us a perfect square, I think we should probably do...
Think about those Pythagorean triples.
Yeah.
That bootstrap Bill got thrown off the boat for. If your radius is 5, if your hypotenuse is 5, what are the coordinates of points that will give you, and this is a great time to pause maybe and ask the students this question as well, but if your radius is 5, if your hypotenuse is 5, what are the integer values of that right triangle? What are the Pythagorean triples? 3 and 4. So if I plug in 3, I'm going to get 4. If I plug in 4, I'm going to get 3. If I
And
plug
because
in
we're squaring, we have the negatives as well.
Negative 3 and 4, and then negative 4 and negative 3. Oh, sorry, 3. There we go. And I believe that works, right? 25 minus 3, negative 3 squared is 9. 25 minus 9 is 16. Boom, 4. So they get that beautiful, I should have done this. I should have done it in yellow, but pink, you know, sometimes the sunrise is pink.
That's true.
Sometimes the sunset is pink. I'm not sure if sunrises are all. I get the probably.
I mean,
right.
sometimes the sun rises red and then blood has been spilt that night.
Ooh. You ever played the game One Night Ultimate Werewolf?
Yes, that is such a fun game.
I'm so bad at it because I cannot lie. But here's a sun. These are not part of the graph. Let me go ahead and get rid of them. Here's our square root function, right? And once again, I said at the beginning, hopefully that you do recognize some of these functions, like x squared, but hopefully some of them were new. And this is often, for most pre-calculus students in this course, a new function that they haven't really thought about. You've seen the circle, but the semicircle function, that's what this is. What would happen if I changed this to like a 49?
Oh, then we would just make our radius bigger.
Yeah. Right?
So
What would it
it'd
be?
What, like 7?
7.
It would have less integers though, but that's okay.
Yeah. 5 is nice just for the purposes of presenting the function. 7 wouldn't be as great because you don't get these awesome Pythagorean triples. RIP bootstraps. All right, domain range 1 to 1. Hit me real quick.
The domain is from -5 to 5, including both.
Mm-hmm.
And the range is from 0 to +5, including both. It is not 1 to 1. Because if you get out like 4, you don't know if you plugged in -3 or +3.
Yep. And we dealt with that a second ago when we were plotting points. It fails the horizontal line test. Our range, our domain is the x coordinates and our range is the y coordinates. All right. We got one last function for you. All right, this one may be review for computer science kids, but this is called the greatest integer function. Okay? You might often see it look like this. And Mrs. Contreras is currently doing it with her fingers. Right, the little floor, little L's, whatever. This function says when you plug a number in, so let's say 4.5, you get the greatest integer that is less than or equal to that number. All right, so there's some less than or equal tos involved. So it's a little bit counterintuitive. Greatest integer function, less than or equal to? Right? It's the greatest number that is less than the number that was plugged in. So what's the greatest integer less than 4.5?
4.
4.
Because it's the
Right.
4.
Let's do some more examples that I got here. What is the greatest integer less than or equal to 3?
It's just 3, right? Because it's less than or equal to.
All right, how about 1.7?
I think that brings us down to 1.
Right. Pi.
Pi is like 3 point stuff. So when we floor that, it's 3 again.
I like how you're using the name of the other name for the function. It's also called the floor function. Right? You're flooring the number. You're like saying, hey, go down to the thing that is less than you. You go down, floor. We also have another function called the ceiling function, which is the opposite. It says go to the smallest number that is above you. Right? What is the floor of -1.75?
Well, we're going down from -1.75, so we need -2.
Boom. All right, this is often like accidentally when people go too fast. Don't go too fast. Think about the math that you're doing and spend time absorbing it. This is -2. This is often mistaken or gotten incorrectly. Right? This is not going to -1, it's going to -2. The largest number less than the number that was plugged in. Let's graph this thing. Let's plot some points. Let's plot those 3 points. So we got 3, we got 3. We had pi, we had 3. We had 1.7, I believe we got 1, right?
Mm-hmm.
Right, we had a negative 1 point and something, we got negative 2. We had negative 1 point something, we got negative 2. And then I believe there was one other one that we plugged in. Maybe not. 4.5 is the one. So 4.5 gave me 4. All right, so we got some points. What's happening here though? Give me some more.
Well, I like 0, so 0, and then flooring that would give us 0.
Yep.
But if you plug in like 1.9999999, you still get 0. So if
you get 1 if you plug in 1.99999. I think you mean to say 0.99999.
Yes.
You still get 0. And just as an aside, it's my goal this year, and it was my goal last year, and I was mildly successful. So always write my decimals between 0 and 1 with a leading 0. I think it's helpful. I think it's a good practice for everyone to not just write 0.134, but write 0.134. And here's an example why. Like saying 0.134 is very clear. And that's something that we strive for in math, is to be clear. So 0.999999999 goes to 0. What about negative 0.00000000001?
That goes down to negative 1.
What's happening at this point? What happens when I plug in 1?
When you plug in 1, you get 1.
All right, and I wonder if I can zoom in here.
Oh, lovely.
That's nice. Then. So at 1, I get 1, right? So what should I draw down here?
You should plot an open circle at 1, 0. Yeah.
And that's
shows we can get infinitely close. But then once we hit 1, we jump up to 1.
Once we hit 2, we jump up to 2. Right? But we need to put this hole here, because if you are like an anarchist and you just like did that, like that's wrong for so many reasons. A, it's not the greatest integer function, and B, it's not a function. And so we don't want to do that. All right, so we're up here, we're going across, hole, jump, hole, jump, hole, jump. And then it's going to keep going. And I'm just going to like, I don't know, I don't feel like drawing the whole thing. I guess I should. I'll do it fast. All right, cool. And then down here, what's happening at this point right here? I guess I want to circle the point, so I'm just giving you the answer.
Oh, nice. Yeah, we have an open circle there.
I was gonna hover over it, but as we've established, I can't do that. And then I believe we're just gonna continue to do this.
It continues down. Yeah. So it looks like it's a staircase, and so you can like climb up the steps.
But don't fall off the ends on each of these steps. That would be
yes.
Not good, because you'd fall forever. You never get hurt. You just reach terminal velocity and then fall forever. So that's unfortunate. You ever seen Spy Kids 2? That happens in Spy Kids 2 to my Spy Kids 2 fans. All right, let me get back to, for all those people that use full width mode, let's get back to full width mode. Domain range and one-to-one.
So the domain, we can plug in any number so that we do have all real numbers. The range is only the integers. So we could do that. We could just list them out, which sounds really tedious, or we could remember the blackboard bold notation.
Boom. Nice. And then one-to-one.
No, I don't think so, because there's an infinite number of inputs that we could have that get out each of those integers.
Yeah. If I want 5, there are many things that give me 5. Right? A one-to-one would be only one thing giving me 5. Cool. We're going to pause for just a second, and we'll be right back. Fly, eagles, fly.
On the road to victory.
Fly, eagles, fly. Score a touchdown, 1, 2.
1, 2, 3.
Hit 'em low, hit 'em high,
As
watch
watch our
those
eagles
eagles fly. Fly, eagles fly,
fly.
on the road to victory. E-A-G-L-E-S,
Eagles.
Eagles. I spelled eagles wrong. All right, let's close this video out. We had a little discussion a second ago. That's why we paused. And we're going to close this thing out here. We have talked about all the parent functions. Any words of wisdom for our students as we impart, or part, not impart?
I think just be careful with all your drawing, with all your plotting and everything. Be careful.
Mm-hmm. Right, and know those points. Know the important points on these graphs. It's not enough to just recognize what the graph looks like. We want you to know these graphs in detail, which is why we spent the time doing this. And then you will have an opportunity to do this yourself if you didn't already as you followed along. All right. So I think we're good. All right. Go Eagles.
Go Eagles.
All right. Yes. Let's close this thing out.
All right.